This lecture we will look at the concept of plane stress and stress transformation. So to kick off, let's look at this first concept of plane stress and what do we mean there. And we'll talk about it really in terms of a case that we've already looked at when we derived our case for general stress. So if you remember when we first brought this up, we had some amorphous body, and it had various loads applied to it in different directions, and then we took a slice and a little tiny cube out of that slice. Put some grid lines on there. We took this little tiny cube out, and we found that for each of these faces will have a normal stress. So normal stress in the x, the y, and the z, as well as a shear stress also acting on every face. And that's a really good general case, and from this we learn that our orthogonal shears have to be equal and opposite to keep the stress block in equilibrium, and this was a really good model for us. However, we can simplify this for a lot of applications in structural engineering. And this is this concept of plane stress. So say I've got a beam here, and the beam has a point load, and these are the two reactions. So if we, looking at the coordinate system here, what we find is that there's really no stress acting in the z direction, and so we only have stresses in the xy plane. Hence, we call this stress state planed. So if we've got this plane case, and so ignore this theta for the time being. If we have this plane case, well, we've got some. We take a little stress block, right out of the middle here, and we draw it on here. Well, we'll have some stress in the y, some stress in the x, and some shear all the way around, and that's great. And so that's not too different from our general case. We've just taken off any stresses acting in the z direction. So there's nothing overly complicated there. Now we've really been dealing with these problems with our bending stress and our shear stress throughout this course. Now we're going to get to sort of the crux of the lecture today, and it's really the second part called stress transformations. So why would we want to do stress transformations? And so I've drawn this this angle here in this inclined plane. And this is really, if we think back towards, think vectors, is going to be the sort of, way to figure out the why we would want to transform the stress. And so by what I mean by think vectors is that if you ever worked with vector addition, you know that for a given force vector at some angle, it's got some component in the y direction and some component in the x direction. And so for most of our engineering applications, we find it's very convenient to break these vectors down into y components and x components. So like when we do our equilibrium equations, we do some of the forces in the x, some of the forces in the y, but really those are acting as a combination, as a vector, and it's really this total vector is the magnitude of that force acting upon the system. So I mean, here on our general case, we've got these forces coming in at some random orientation, but there's a component, in each of the principal axes of these. It's a vector added up there. So if we're talking stresses instead of forces, Well, really what we care about is whether the material is going to be able to withstand the loads we put upon it, and will those stresses be below some critical aspect. And for us, and analytically, it's quite convenient to break these stresses up into, x directions and y directions. But the material really doesn't care. The material cares about the total magnitude. And so what we need to do is really, search for, well, what is the biggest stress there? And that biggest stress is going to be some combination of, x's, of our normal stresses in the x and the y, and our shear stresses. And if you think about a vector, well, these are all acting at some, angle theta. And so in order to find that, well, we sort of, you can think about, well, we rotate this block around by some angle theta, and as we rotate that angle around, our normal stresses and our shear stresses will, the total vector will change, but the components of each will modify until we can find, perhaps our largest normal stress or our largest shear stress. And that's really what we're going to do, is lay out some of the mathematics to help us do that. But again, and there'll be a fair amount of math in this lecture, so I hope you don't get lost in it. But the thing to keep in mind is really what we're doing is we're rotating this little stress block around in order to find our largest normal stresses and our largest shear stresses, just like we would, with a vector. All right, so launching off from there. So if we're going to rotate this little block around, well, that's really sort of similar to if I took a slice through this block at some angle theta, and I was looking for, well, what is the equivalent normal force on that slice, and what's the equivalent tangential force on that slice. So let's just do that. We'll draw this out, and we'll draw a free body diagram, and what we'll look at is what are the equivalent forces for both, in the x direction and in the y direction, and normal. So bringing this over here, let's draw our free body diagram of the plane. And so it's going to be something like that. So this is going to be in the x direction, and the x direction is really this this full height here. In the y direction, because we've taken at some angle, this little area is going to be smaller than this area, and I'll write that one out for you. And then we'll draw this in 3 dimensions just to kind of help us visualize. All right, so we know that there's going to be some force acting normal to the surface, and we'll just call that Pn for the normal direction. And there's going to be a force acting tangentially, and we'll call that Pt. In the x direction, well, it's just going to be this stress times this area. So where this area is A of this block. So in the x direction, we have sigma x times A. The shear in that direction, again, it's just going to be this shear multiplied by the area that it acts over. And so that's just going to be tau xy times A. Now when we go to the y direction, like I said, we're going to have a little bit smaller area here, so we have to reduce that accordingly. And this is really the same as, well, if we use our trigonometry. Well, if we have some angle theta here, and we think areas, well, the tangent of theta equals the opposite over the adjacent, so we can then solve for that, and then get what our equivalent area is down here. And if we do that, well, we have sigma y times the area times tan of theta. And similarly for our shear stress, it's also acting on this smaller area here. So if this area is A, this area is A tan theta, and this inclined area is A divided by cosine theta. And you can work out the trigonometry there to convince yourself if you so desire. So this is xy times the area times the tangent of theta. All right, well, now we have all of the equivalent forces here. If we want to solve for Pn and Pt, all we need to do is set up our equilibrium equations, and so let's do that. So we'll draw just this little line here just to keep our calculations separate from our drawing, keep things a little bit neater. And let's find the sum of the forces in the normal direction. And that equals 0. So this is normal to the cut of the plane. So adding everything up, we get Pn, and that's going to be minus the sine of theta times sigma y times A times the tangent of theta, so just sine of that, minus cosine theta times tau yx times A times the tangent of theta, as well as we minus sine of theta, the shear stress xy times A minus cosine theta sigma x times A, and all of that equals 0. So feel free to pause the video and work have a work out the trigonometry there if you find that confusing. But if we simplify all of this down and we solve for Pn, what we find, Pn equals the sine of theta times sigma y tangent of theta plus tau xy plus we'll draw it down here, plus cosine of theta times sigma x plus tau xy tangent of theta, and all of that is times this area, so just factoring out this area here. So that's what Pn equals. And then if we sum our forces in the tangential direction, we will end up with something very similar. So let's just work through that real quick. So we get piece of t in the tangent direction minus cosine of theta, and that's all going to be times sigma y times the area times the tangent of theta, and then plus sine of theta tau xy a tan theta minus cosine of theta times tau xy times a plus sine theta times sigma x times a. If we simplify all of that down, then what we end up with is piece of t equals cosine theta sigma y tan theta plus tau xy minus sine of theta times sigma x plus tau xy tan theta, and that whole thing is times the area. So that gives us forces. And again, and I'll do this throughout the lecture, just try to remind you of what our whole goal is. So the forces is well and good, and that's a lot of trigonometric functions, and you kind of go, Lucas, like, all right, well, I guess that's true. But remember, what we're looking for are what these stresses are going to be at this inclined angle, because we're looking for what these maximum normal or maximum shear stresses are going to be. So in order to do that, so now that we have forces, well, we need to turn this into a stress. So we have forces Pn and Pt. We want stresses sigma theta and tau theta. So like I said, we want to turn these forces divided by this area into our transformed stress. So in order to do that, all we need to do is go our normal stress at this angle is just going to be Pn divided by the inclined area, just this force divided by this area, and that equals Pn over A divided by cosine theta. And similarly, if we want to look at the shear stress, tau theta, that's just going to be piece of our tangential force divided by the inclined area. And that's again equal to piece of t divided by A divided by cosine theta. And then the last sort of trick to this is that remembering that, so we'll just put a little note, going back to sort of trigonometry, is that tan theta equals sine theta divided by cosine theta. And so why do and I'll just put that in little bracket. So why do I do that? It's like, well, we have a lot of tangent thetas through here, but we also have sines and cosines. And so being able to simplify this, we can use we can use this fact and then we can simplify things down. So I'm not going to work through all of the algebra. I can post a derivation if that's desirable. But really what I'll do is we'll just jump through. So Pn, we're going to take this big equation and divide it by a divided by cosine theta. And for tau of theta, we're going to take this big equation and we're going to divide by a divided by cosine theta. And we're going to turn all of these tan thetas into sine theta divided by cosine theta. And if we do that, we end up with sigma theta. So remember, this is the normal stress on this face. Sigma theta equals sigma x cosine squared theta plus sigma y sine squared theta plus 2 times tau xy cosine theta sine theta and similarly, if we take our piece of t and we divide by a divided by cosine, we end up with tau of theta equals sigma y sine theta times cosine theta plus tau xy cosine squared theta minus sigma x sine theta cosine theta minus tau xy sine squared theta. So these are still pretty big, unwieldy equations, and if we can simplify them further, that's even better. And so what we do is, we can use the following trig identities to simplify these even further to something which we'll be able to work with and do some a little bit more useful mathematics on. So if we use these identities, sorry, I had trouble spelling today. These are sine of 2 theta equals 2 sine theta cosine theta. The second one is that cosine of 2 theta equals cosine squared theta minus sine squared theta. 3 is cosine squared theta equals 1 plus cosine of 2 theta over 2. And the fourth trig identity is that sine squared theta equals 1 minus cosine of 2 theta over 2. The reason we're going to use these trig identities is we're going to do a little bit of calculus, and it will simplify these equations into something which is going to be much easier to use. So if we plug these in, and you can start to see some of the patterns here. We've got a cosine squared, a sine times cosine, a sine times cosine, and look, we've got two of those. So it looks like we're going to get everything in terms of really 2 theta. And if we do that and we plug those in, these two equations simplify down to sigma theta equals sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times cosine of 2 theta plus tau xy sine of 2 theta and our tangent of x is going to be equal to sigma y minus sigma x over 2 sine of 2 theta plus tau xy cosine of 2 theta. So those are slightly easier equations to work with than, these big sort of gobbledygook ones. Let's have a look at that and let's find out, how would we use those? And let's just do a really quick example. Let's have this example where we have just a bar. And we're pulling this bar with a force P, and we have some little stress block here in the middle. So if we draw that stress block, it kind of has a boring stress state. It's got sigma x equals P over A, and then tau equals 0. So it has no shear stress. So this is just pure uniaxial pull. And what we want to do is transform the state of stress by 45 degrees. So really, we want to go from something which is sort of this uniaxial tension where we don't see any apparent shear stress, and let's rotate it to something that looks like this, where there'll be some normal stress, and this is again all going to be at 45 degrees, as well as there'll be some shear stress. Oh, that one's drawn the wrong direction. Some shear stress, so maybe highlight that in red to make parts of that look a little bit clearer. And as I said, this is more an illustrative property just to kind of show how this will work. So if we're going to do that, well, here's our two equations that we're going to use. Really all we're going to do is, well, we've transformed it by 45 degrees, so we just need to throw in 45 degrees into theta, and then we take our x and y, normal stresses, plug them in, and our shear stresses, and plug them in. So we'll show you how that works. And as I said, this is a very simple example, but it's really just to illustrate how these equations would function. So if we've got sigma theta equals sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine of 2 theta. Well, then if we plug stuff in, we're going to equal sigma x. There's no stress in the y, so that's plus 0 divided by 2 plus sigma x minus 0 over 2. Cosine of 2 times 45 is 90, so that's just going to equal 0. So that's times 0. And there's no shear stress, so that's also plus 0. So we find out that our sigma at 45 degrees is just going to equal sigma x divided by 2, which is equal to P over A divided by 2. Similarly, if we work out our shear stress, you've got tau xy, and this is at, tau xy, that's at tau at 45 degrees. We get sigma y minus sigma x divided by 2 sine of 2 times 45 plus 0, which is our, that's plus tau xy, but that equals 0 times cosine of 2 times 45 degrees. Xy equals 0, so we end up with tau xy equals negative sigma x over 2. So it's just going to go the opposite of how we've drawn that. And really, what our stress state ends up looking like is just, so if this is our little stress block at 45 degrees, well, we have some sigma x over 2, sigma x over 2, x over 2, divided by 2, and then we also have some shearing stress. Also, tau equals sigma x over 2. Now, I mean, it's not an overly exciting example, but it does kind of illustrate a point that, because we're looking at, this stress transformation and rotating, say, a little stress kind of through a circle, we find that even for our, for our uniaxial tension example, while in our coordinate system for x and y, we've got 0 shear stress apparent, there is a location where there is shear stress present just simply by pulling on this. And so that's important when we start looking at how these materials fail, where ductile materials tend to fail in shear and brittle materials tend to fail in tension. And so this is a way for us to really kind of identify, what's going on, and are we likely to get, and can we use this information to understand at what stage we will see failure. So, as I said, this is all well and good, and I'm sure you're thinking like, Lucas, all right, well, that's a bunch of math and a pretty easy example, but why would we do this? And it really does come back to this notion of looking at failure. And it's what we'll be leading up to are these failure criterion, which we can use our different stress states to determine whether or not those will occur. So, and this is really, if we think about our materials really as ductile and brittle, ductile materials fail in shear, and brittle materials fail in tension. So For a ductile material, yeah, this is a big deal for us. So we might have a beam which really has relatively small shear loads on it, but there'll be at some there'll be areas of high shear where our material's trying to slide past itself that we want to know about. This is for say like a simply supported beam. And so that's a big deal. For the brittle materials, this is a really big deal in concrete. So if you've got, you can think of that. This is all cracks in concrete do this. So if we're bending a concrete beam, and I'll draw it exaggerated here. And it's going to have some cracks, but those cracks will start off here in the middle, more or less up and down, and they're really flexural cracks. But then as we get towards the supports, those cracks will start inclining into more shear oriented cracks. And really what's happening is that as we move across this beam, we can think about it like there's a series of these little stress transformation blocks occurring, and the angle of the normal stresses. So if we kind of draw something like that, you can think, well, there's these little stress transformation blocks, and this is the direction of our main tension forces as we go through, and they get steeper and steeper as we get towards the ends, and so until so that we're more or less horizontal here, and then we're pulling in shear, or we're pulling at an incline as we get close to the supports. So this is a really powerful tool for us, particularly when we're doing more detailed analysis of structures. And so what we really want to know is less about, well, what's the stress transformation at a particular angle. Rather, what we care about is, well, at what location, at what angle are we going to have these maximum tensile stresses? At what angle are we going to have the maximum shear stresses? And what are the values of those? And so I guess, again, maybe a way to sort of, to write it explicitly is, the question is, we've kind of, as I said, we've learned about everything like this. I'll say this is the how we've been taught, but really what we care about is at some angle, and I'm just going to call that sigma p. There's some sigma 1, sigma 2, sigma 1, sigma 2. This is there'll be some orientation where we'll have our max and min normal stress. And then there'll be some orientation where we will have, and I'll call this sigma s, where we will have our maximum shear stress. Now, yeah, I'm writing tau max here. Don't get confused with the tau max from our shear distribution. Think about, even at that location of our maximum shear stress, well, there's some orientation by which we have our maximum shear. And so this is our max shear stress. So, and what I've drawn here is, sigma 1 equals sigma max, sigma 2 equals sigma min. And remember, all of these are equivalent. We're just changing orientation, so think about this as really just a vector problem. Other really quick thing to note is that, for our principal stresses, again, thinking vectors, for this to be a maximum and this to be a min, we actually find that we have no shear stress here. And that's really what we're seeing with this cracking, where that's just sort of pure tension pulling that across. So if we want to find out, at what, where we have a maximum occurring for a given function, well, what do we do? Well, we use a little bit of calculus where we take that function, we find its derivative, and we set that derivative equal to 0. And so that's what we can do, is we can take for both our normal stress and our max shear stress. Well, if we want to find the angles at which they occur, well, we can take these equations, sigma theta and tau theta. Well, we can find the derivative of sigma theta, set that equal to 0. We can find the derivative of tau theta, and we can set that equal to 0. And then we know the orientation at which these will occur. So I won't go through the math there just for time's sake, but we can find that for tan theta, so this is the, take d sigma d theta equal to 0, you're going to end up with the tangent of 2 theta p equals 2 tau xy divided by sigma x minus sigma y. And then if you take d tau over d theta, and we set that equal to 0, we end up with the tangent of 2 theta s equals sigma y minus sigma x over 2 tau xy. The interesting thing, these are opposite reciprocals of each other, which means these are 45 degrees apart. So kind of just by definition, we can find out that the the angle by where we're going to have our maximum shear, our maximum normal stress, is going to be 45 degrees from the angle where we're going to have our maximum shear stress. So, well, now that we know the angle that these occur at, we really care about, well, what are these values? Well, all we can do now is we can take, we can solve for our tangent of 2 theta p, and then plug that angle into this equation, and we can find out what our our max and min normal stress are. And then we can also do the same thing for we can solve for this angle 2 theta s, and then plug it into our tangent equation. And if we do that, what we end up with is sigma max, sigma min, and that's just going to equal sigma 1, sigma 2 equals sigma x plus sigma y divided by 2 plus or minus sigma x minus sigma y over 2 squared plus tau xy squared. So just, for reference, sigma 1 is going to be our maximum normal stress, sigma 2 is going to be our minimum. And this is just by convention. And then if we do the same thing where we plug in this angle into our shear stress equation. Oh, and we also find out that if we do the same thing for our, put theta p in, tau of theta p equals 0. Then we can also find out that at theta s, tau max equals sigma x minus sigma y over 2 squared plus tau xy squared. Which is interesting. This is all very similar to what we have up here, and I skipped over a whole bunch of the algebra and the trigonomics there, really just for brevity. I can post the sort of more long-winded derivation of that, but this is the gist. Where what we wanted to do is we wanted to start with a given stress state in the x and y direction, and we wanted to find, at what point do we have our maximum normal stress, and what point do we have our maximum shear stress, and what are the values of those two? And it's really this set of equations here will do that for you. These two will find the angle which you have to rotate in order to find, go from a stress state like this to either your maximum normal stresses or your maximum shear stresses. And then these equations here will tell you what the values are. So for our maximum normal stresses, it's just right here. And for our maximum shear stresses, it's just right here. And I think just one last bit that if you also plug in, so as I glossed over it briefly here, so at our principal stress, so this is sigma p, at our principal stresses, we found we had tau equal to 0. I found tau max here for at our angle of maximum shear stress. Well, if you also work out what your normal stress is, so tau at theta s actually equals sigma average sigma x plus sigma y divided by 2. It's just the average of these two. So that's really all of the equations to be able to do this, and this is fantastic if you are, if you've got access to computing powers, it's kind of annoying if all you have is sort of your own calculator, and it's really annoying if you don't have any calculator and you've got to do all of this by hand. And so what we're going to do, this is really just laid all of the mathematical foundation, and to sort of show that these things are real and sort of a derivation of it. But in the next video, what we're going to do is provide a more user-friendly ability to use these equations and in order to find out the things which we really care about, which are really important, are our magnitude and orientation of our max and min normal stresses. Also, so this is our principal stresses. And our maximum shear stresses. All right, so with that, that's going to conclude this lecture.